Hi! In this video, you will learn that there exists a magic trick to make matrix computations really easy. Remember diagonal matrices? They are the most simple matrices to work with. You will learn that a lot of non-diagonal matrices can be diagonalized and are then called diagonalizable. Let's first see in which situations you might encounter a diagonal matrix. Suppose you are studying the rate of growth of two types of cells. Suppose you know that the first cell type splits into 2 new cells every day and the other type splits into 3 new cells every day. You want to compute the total number of cells after 20 days. Mathematically, the cell division looks like this. AK is the number of cells of type 1 on the kth day and the same for BK. Each day, you multiply the number of cells from the previous day by the right number. This is called a recurrence relation. Using a matrix and vectors, you see you can rewrite the recurrence relation like this. The vector AKBK is equal to the matrix 2, 0, 0, 3 times the vector AK-1, BK-1. Or, even shorter, as xk is equal to the matrix A multiplied by the vector xk-1, where the vector xk has components AK and BK, and you can see that A is a diagonal matrix. Suppose you started your experiment with 4 cells of type 1 and 10 cells of type 2, then this means A0 equals 4 and B0 equals 10. So the vector x0 is equal to 4, 10. Starting with 4 cells of type 1 and 10 cells of type 2, the number of cells of each type on the first day is equal to x1, which is equal to A times x0. After 2 days, it is A times x1. This you can also compute like this. A times x0. And after 20 days, then it is equal to A times x19, which is equal to A times x18, etc., until you multiplied A 20 times with itself and apply it to x0. You can check for yourself that it is equal to this simple expression. Piece of cake, right? In another situation, the recurrence relations could be more complicated. For instance, they might look like this. AK is equal to 6 times AK-1 minus 2 times BK-1. And BK is equal to 6 times AK-1 minus BK-1. Here you need both AK-1 and BK-1 to compute either AK or BK. This is called a coupled system. Writing this in matrix form is not the problem. xk is equal to A times xk-1. And now A is the matrix 6 minus 2, 6 minus 1. But computing x20 is. Actually, doing the matrix multiplications 20 times is hard work. Why is this harder than in the previous example? Well, in the previous example, the matrix you used was a diagonal matrix, and now it is not. Being a mathematician, I am quite lazy. So normally I would let a computer do the computations for me. But what if I want to find a general formula for xk without specifying k? Then the computer cannot help me either. So then, I live by the following rule. If not strong, then be smart. Make the situation easy. Here is the magic trick. Change the coordinate systems for the axes. What does this mean? Well, pick some invertible matrix P, such that xk is equal to P times yk, and so yk is P inverse times xk. Now xk is equal to A times xk-1, so substituting pyk for xk, you get pyk is equal to A times P times yk-1, which is equivalent to yk is equal to P inverse AP times yk-1. So what, you would probably say? Well, here is how smart you have been. If in our example you take the matrix P equal to 1, 2, 2, 3, then you can compute P inverse AP, but only if you stop the video now and take your time to do the calculations. Hey, it's a diagonal matrix! So finding a formula for yk is easy, just like in our first example. So you found yk now, and because xk is equal to pyk, you can compute xk from this. Does it feel like I have cheated on you by coming up with this magical matrix P? Is it always possible to find such a matrix P that does the trick? Let's first explain what the trick was. You started with a matrix A, then you came up with a matrix P, and it turned out that P inverse AP is a diagonal matrix, which made things a lot easier. A matrix A, for which you can find such a matrix P, is called diagonalizable. You really have to come to class if you want to find out which matrices are diagonalizable and how you can construct a matrix P. See you there.